What we are responsible for with my teams is, among other things, bringing the recommendations on the page. So when you go to the product page, down here you have actually two kinds of recommendations. So one is the are similar items, and the other thing is what we call cross-sell, right? So items which are not from the same kind, but which might fit. So for this shoe, for example, there's a number of jackets down here. So this is like the main thing we do, but we also produce recommendations for many other parts. Like if you get a newsletter, down there are also recommendations which are also served and computed by us. And the interesting thing, so this thing is fully data-driven, right? So it's not, so we have so many items, you cannot actually have people, by hand manually mark what are similar items, but we're just taking in what users are looking at, and we're doing a bit of data analysis on that, and then we automatically get this thing which is updated several times per day, right? So that's a lot of data, 4.5 million, that's about 50 visits per second. And so the question is, or what I want to talk a bit about in the brief time I have is, like, so how do you approach something like that, and what kind of algorithms do you take? Does it need to make that kind of computation scalable? Okay, so like in a nutshell, how does recommendation work? So we have a user here who is browsing on our website, and what we do is we collect all of the activities that he has, all the catalog views, all the product views, like also how he moves from the item to another item. And then of course we have also for each of the items we have many different attributes, like which brands they are, which color they are, what kind of item they are, and so on. And then of course something magically happens down here, where we take in like everything the user did and the information we have about the thing, and then for that we produce for each item the recommendations which you put in the database, and then when you go to the website, actually that's how we get this stuff, right? So it's not really, so it's sort of, this process here is too expensive to do this in real time, but it's rather processed every 4 hours, and then we have, for all our articles, we have the ones which we show up here. Okay, so the question is actually what happens down here. There are many different things you could do, from very simple things to very complicated things. So the standard, which everybody starts with, is so-called collaborative filtering. So where you sort of you don't really look at this, but you're mostly looking at the user data. So you're looking at, for each user, at the profile, which items he's looked at, and then you see whether there are similarities between these profiles. So are there items which have been looked at together by the same kind of users, and that gives you some kind of similarity, and that already works remarkably well, right? So that's called collaborative filtering. Then there's another type where you sort of say content-based recommendations, where you look what the user has looked at, but then you go through the attributes. So you say if a user has looked at this brand very often, then maybe he likes this brand, so I'm going to show him other stuff. Right, and that's like the different ways, and you can spend more and more time, and sort of what everybody is looking at right now is personalized recommendation, that you just not only get like the kind of items which all the users like, but specifically tailored to you, right? And to do that, you really can dig down here and then do all kinds of machine learning, really trying to figure out for each individual user how to best predict the kind of item he's interested in. Right, and this is where it gets interesting. So just crunching this thing here, like the logs, and sort of making these statistics, who looks at this, who has looked at something else, that's still something you can do fairly well, like even with standard database technology. But for all the millions of users and hundreds of thousands of items you have, for each user getting a personalized recommendation, that's where it gets interesting down here. Okay, so what kind of technology do we actually have? So, and to make this scalable, right? So it used to be, I don't know, 20 years ago, if you wanted to parallelize an algorithm, if you want to scale it, you really went down and you thought about it and you programmed everything by hand. But luckily nowadays, we have technology for that. So, and as you probably all know, so the main thing is Hadoop, which sort of looks like this. So down here, the red blocks, these are the actual servers. And based on that, you have a distributed file system. So you can just put files in there, and then Hadoop takes care where exactly these files are put. So you don't have to think about it together with replication and everything. And then based on that is sort of the compute layer, which also distributes your computation, right? In a way that the data also doesn't have to be moved around, but sort of the idea is the data stays close to where it is, and the computation moves to your data. And then based on that, you have your application, your recommendation algorithm or whatever, which sort of drives the whole thing. Okay, so we start with the user logs. We put these on HDFS. And then sort of what you can do with it is what's here on the right-hand side. So this might be, let's say, a segment of your user logs, and this is just the data. And then originally, you only had like 2 operations you could do here. One is like a map operation, where you take each data point and apply the same operation to them and get a new version of that. And then the other thing was this reduce operation, where you take all the data that you have, and then you sort of combine the data you have until you get the final result. Right, so here you could, for example, for each item you could count which user has seen that, and then down here you're sort of aggregating all this information so that you have the recommendations per item. Right, so this is was already quite powerful, but then people found out you can do much more, like filtering or even join operations, like in a classical database where you have 2 tables and you're sort of trying to match the different data items you have and so on. And now a system like Spark or Apache Flink, sort of you have a very rich language for expressing all kinds of operations, and then these scale automatically, right, which is very nice. Okay, but still, so the question is now, so this is all more like from a database point of view, but how does it actually fit together with machine learning? Because in any kind of large-scale learning, machine learning, usually you have a process which looks like this. So you start with the raw data up here, right? Or with actually you have the data which first sits somewhere, and then the first thing you have to do is you have to get the data. You have to talk to database people and say, please, give me a dump of your data so I can do some data analysis with that. So that's already, sometimes takes a long time. And then you end up with raw data, but raw data itself is not really useful. So first you have to extract features from that. So mostly numerical features, do some simple statistics, collect a lot of those, and then finally you can feed those into the learning algorithm, and then you get your model which does prediction on future data, for example, predicting correctly which the items are which are interesting for a certain user. Okay? And now if you sort of, the question now is how do we bring this together with this? Right, so this is like the kind of stuff we can scale well. This is like the pipeline we want to put on that. And it turns out there are many operations in here, like data extraction, doing this feature extraction, which really fits this kind of approximation well, right? So taking the raw data and then computing these features, you can imagine that's something which is quite straightforward. So you're just doing counts and stuff like that for each user individually. But it turns out that these learning algorithms, that's really the hard part. So this is not something where you can just take an algorithm which you have always used and sort of bring that on a system like Spark. But here is really the thing where you have to find new algorithms which are sort of different from the ones we had before, but which are very scalable. And this is what I want to talk a bit about here. And of course, this is very, very complicated, but so the main insight, that's what I'm trying to share with you. And I'm not going to tell you what it is until we come to the end to spoil the surprise. Okay. So, so in a nutshell, so what does machine learning look like in a nutshell? Okay, so it's always like this, that you have some input data X, right? So this is like the table where you sort of all the data points are in here, and then you have some output Y. So think about this in the recommendation setting. So X might be all the features you computed for each of the users and the items, and Y is sort of the how likely or how interesting this item would be to the certain user, right? So and this is just the raw data which you've collected over a long time, and you already pre-processed that. And then what you want to learn is sort of a model, some function which takes an input and produces this output. Right, and machine learning means sort of that you don't actually know what this function is, but instead you have like a class of functions which has a very large set of parameters which can model all kinds of mappings from here to here. But sort of you want to take the data to adjust these parameters in a way that you make very little prediction error, so that you're doing this like the prediction from here to here with very small error. So you also have some way of measuring how big the error is. Okay, so in a way, machine learning, there's no intelligence really in this. It's mostly like an optimization problem. So it all boils down to an optimization problem. Okay, and so the question is, can we take something like, what about these operations here? Can we optimize? Can we solve the optimization problem as a machine learning problem well? And of course, so optimization, that's like really, really old topic in mathematics, operations research, and everywhere. So, but it turns out that there's some way to do this which is very simple and can also be parallelized well, and that is gradient descent. Okay, so the idea here is, so this is sort of like the way I think about these optimization problems. So in reality, we had these models have many, many parameters, like thousands, 100,000s. But for each setting of a parameter gives you a certain error on your data, right? So what this sort of means is, so there's some space here, which in this case it's just 2-dimensional, but it could be much higher dimensional. And for each point, I'm getting a score, which tells me how well the model fits to the data. And these lines are sort of the parameter sets which have the same error here. And sort of what I'm looking for, I'm trying to find in this parameter landscape, I'm trying to find a point which minimizes the error, and then that's a model which fits my data well. Okay? And a very simple algorithm to solve this is a gradient descent. So you start at some point, and then what you're doing is you're looking at the derivative of your error, right? So you're at some point, and then you can mathematically say, so if I go in this direction, how much does my error change? Or if I go in this direction, and then the gradient sort of points in the direction where the error goes down the most. And then what you do is you do a small step in this direction, and you do this again. Okay? So in a way, so from a mathematical point speaking, this is a very dumb algorithm, which converges, it's known to converge very slowly. But the nice thing here is that it's very efficient. So for many algorithms, computing this gradient sort of is doing one prediction and then summing up some formula based on the prediction error, right? So it's very simple, and that's something which you can parallelize well. Okay, and you can even go one step further and say you don't even consider like the error on the whole data set, but just the error on a few points or even just 1 point, and then you do this over and over again. And then over time, you will sort of go down here. So you might also go up sometimes, but go down. And in the end, you're just here. Okay? So it's like, so like mathematically speaking, the real optimization problems, they have algorithms which are very sort of efficient, but they don't parallelize well. And so on the other hand, if you do something very dumb, you have an algorithm which can be parallelized well. Okay? And that's actually what people do. So if you look at like MLlib, the machine learning library from Apache Spark, it's all based on gradient descent in some form of stochastic gradient descent. Okay, so you just plug in your model, each different learning algorithm in the end corresponds to an optimization problem, and then you do gradient descent, which is something which you can parallelize very well. Okay, and so now the sort of the message here, the interesting thing which happens here is that the approach to scaling out these complex data analysis algorithms is different from like everything else or which you do on big data systems when it goes to database operations. So right, so you can also, using this map operation, fit operation, you have sort of like the same set of operations as you have with classical databases, right? And they found a way to do this kind of computation in a way which is very scalable. But essentially, they're computing the same thing. But the approach for machine learning is different. So you don't just take the old algorithms and try to make them scalable, but actually using new algorithms, right? And the question is, why can we do this? So why can't we just say, right, so we have the training data, we will try to learn a model, and learning this model is an optimization problem here, and we can just say, instead of solving this optimization problem with the right algorithm, we're sort of approximately solving this algorithm with a different algorithm, right? So why can we just say, I'm not solving this problem, which is very hard, I'm just doing something simpler, because that can scale well. So this feels like cheating in a way, right? Okay, and the reason for that, and that sort of is my main message, which I trying to bring across, is, so the main thing is the following. So this learned model, which you try to learn, this is not the real problem you're trying to solve. So the problem you're trying to solve in machine learning is you start with some data, you want to learn a model which works well on future data, right? So I take the last 3 months of user interaction, and then I want to have a recommendation which works well tomorrow on the users which come in tomorrow. And how I do this, so as long as I have something that works, I don't really care how that works. And this optimization problem down here, right, this is sort of just a proxy for solving the problem up here. So if I find something, and that's the thing, so experimentally people have found out if they use gradient descent, very dumb methods, but which can be parallelized well, it still works well if you have a lot of data. And sort of that's the difference here, right? So it's not just about algorithms, it's not just about parallelizing stuff we already know, but it's really about finding new ways which are also more scalable in future data. Yes. So in a summary, large-scale complex data analysis problems often have billions of examples, millions of features. Many parts of that, if you think bad of this machine learning pipeline, many parts can be parallelized well. The hardest part is the training the model. And here the approach is always to use approximations to reduce this to a problem which is much easier to solve. Yes, because the goal is to generate good predictions on future data. Okay, so this is like in a nutshell everything I could say to that in 15 minutes. If you want to learn more, so you should really try to learn about gradient descent, stochastic gradient descent, and have a look at, for example, the machine learning library which comes with Apache Spark, which is really built on these algorithms. Thank you very much.